Hey everyone, welcome to the Chapter 4 lecture for Chem 100, which is all about organic chemistry. So we're starting to get into sort of the second unit of the class, which is all about organic chemistry, which is basically the chemistry of carbon-containing compounds. So in a minute, this not so polite chemistry meme will make a little bit more sense to you. So organic compounds are those that contain carbon, really that contain carbon and hydrogen, and then maybe some other nonmetals thrown in there. Oxygen, nitrogen, sulfur, phosphorus, a halogen like chlorine or bromine are all common. Quick pop quiz question for you from the last chapter. What type of bonding do you think is prevalent in organic compounds? Ionic or covalent? Hopefully you said covalent, because all of these are nonmetals, carbon, hydrogen, oxygen, nitrogen. And when you have two nonmetals bonded together, they form a covalent bond, not an ionic bond. So a quick practice question for you. Just based on chemical formula alone, are these compounds organic or not organic, or we would say inorganic? The first one, KCl, all right, that's potassium and chlorine. There's no carbon there. If there's no carbon, it is not organic. The second one has 4 carbons and 10 hydrogens. Carbons and hydrogens are the definition of an organic compound, so that one is organic. The second one here, carbon, hydrogen, oxygen, hydrogen, those are all things that are covalently bonded and contain carbon and hydrogen. And then the last one, CaCl2, although there are these C's there, those are not carbons. It's part of calcium and chloride. There's no carbon in this molecule, so it is not an organic compound. All right, so the reason there's this whole field of organic chemistry, that carbon is so special to have its own field, is because, I'm going to see if I can click on this. I don't know how to get rid of my pen now. Help! There we go. Got my cursor back. So carbon is really special, and there's this cute little cartoon video that we're going to watch in order to see why carbon is so special.
To get to the heart of the global warming story, the very heart of it, you've got to look past lonely polar bears, and past melting glaciers, and past the changing climate, because behind the scary news and the very scary Hollywood movies, it turns out that the scientific explanation for global warming depends to a very large degree on one particular atom, the atom that we call
carbon.
Right.
Hi.
The more you know about this atom, the more you're going to know about global warming. First of all, it's everywhere. The lead, we call lead in the pencil, it's not lead, it's
Carbon.
diamonds.
Carbon.
You?
Me?
Yeah, you. You are mostly water, but if I squeeze you like a sponge,
Like a sponge. Yeah.
your dry weight, what's left of you, you're about 2/3 carbon.
Great. Carbon's great, but can I have my everything else back? Please?
Yes, carbon is the central element of life. So much so that everything that is alive, and I mean everything, from an amoeba to a whale, from a dandelion to a redwood tree, in fact, inside every cell, in every creature bar none, you will find
Carbon.
And why?
Yeah, why?
Because as the science writer Natalie Angier says, carbon is the duct tape of life. It stitches living things together. Carbon atoms are built to attach, to grab on to other atoms. They have, as you see, 4 points of attachment, and they love attaching. They can form jungle gyms. This is the inside of a diamond. They form sheets. This is graphite in a pencil. They form spheres. They are very social, which is why they are so suited to living things. Living things, after all, come in all kinds of shapes, and carbon can make them all. but it's carbon's special ability to grab on, to grasp other atoms that is now getting us in trouble. What starts down at the atomic level can, if we're not careful, lead to big, and I mean very big, problems. And in this series, we're going to show you how. So stay tuned for Part 2, Making Carbon Bonds, Part 3, Breaking Carbon Bonds.
And we're not going to watch any of those other videos. So that video series is all about carbon, and particularly carbon dioxide, which is a greenhouse gas, which is technically not an organic compound because it's just carbon and oxygen. There's no hydrogen there. But it gives you that cute little video explaining why carbon is so special. It's because it can make those 4 different bonds. It can bond to 4 different things. And because of that, it can make lots of differently shaped molecules. And that's what living things need, a variety of different shapes and complex molecules. So the 4 important classes of biomolecules, these organic compounds that are really central to living things, are proteins, carbohydrates, lipids, and nucleic acids. DNA is a type of nucleic acid. And that's really the topic of the final unit of the class, or the third and fourth units. I can't even remember at this point. But the biochemistry portion of the class is going over these different biomolecules. We have to understand some organic chemistry first, some basics, before we can really discuss the chemistry of these larger, more complex types of organic molecules. So, get my cursor back. Here we go. So the simplest type of organic compound is a saturated hydrocarbon. Hydrocarbon literally means it's made of hydrogen and carbon. And saturated means that it has all single bonds between the carbons so that the carbons are saturated or bonded to the maximal number of hydrogens they can be. So we call these saturated hydrocarbons alkanes. And there's a lot of common alkanes that we use. Alkanes are often used as they're a good fuel source. We can combust them, burn them with oxygen for fuel. So you might use propane in your stove if you have a gas stove. Propane is a 3-carbon alkane. When you fill your car with gasoline, you fuel your car with mostly octane. There's like different levels of gas, and they have numbers like 87, 93. We're just talking about the percent octane in the gas. And so that would be an alkane with 8. Octo is 8 carbons. So some basic chemistry, we talk about sort of polarity that we left off with in chapter 3. Alkanes are non-polar because they're made of all carbons and hydrogens. And so remember, carbons and hydrogens share electrons equally. And when electrons are shared equally, you get a non-polar bond. And if you're a molecule that's just made up of a bunch of non-polar bonds, then you're a non-polar molecule. And this will become relevant in future chapters, so we definitely want to remember this fact, that alkanes are non-polar compounds. So alkanes can be straight chain, where all the carbons are linked in a row, or they can have branching chains, where the carbons some of them are linked in a row and some of them branch off. Or they can be cyclic. We call these cycloalkanes, where the carbons are linked together. Notice that in all of these, the carbons make up the center or backbone, and the hydrogens stick out of the periphery. So the general formula for an alkane, a straight chain alkane, is CnH2n plus 2. So for example, C4, if a carbon has 4, or if a alkane has 4 carbons and it's straight chained, then it's going to need to have 2 times 4 plus 2 hydrogens. 2 times 4 is 8, plus 2 is 10. So this would represent a straight chain alkane, all right? But what about for a cycloalkane? Well, if we go back to this previous slide for a second, and we look at this cycloalkane here, it has 4 carbons, so the molecular formula would be C4, and it has 2, 4, 6, 8 hydrogens. Each of those carbons is bound to 2 hydrogens. So if we wanted to turn that into a generic formula, we would say that a cycloalkane had a generic formula of CnH2n. However many carbons there are, each carbon is going to have 2 hydrogens. And so this would be the formula for a cycloalkane versus the formula for a straight chain alkane. So we could have a problem that gives us the formula of some alkanes and just asks us, is it straight chain or is it cyclic? Is it a cycloalkane? And we can tell based on whether it fits this formula or this formula. So C4H10 was actually the example I just gave for a straight chain alkane because 10 is 2 times 4 plus 2. Whereas C6H12, it's just the number of hydrogens is 2 times the number of carbons. So this would be a cycloalkane. It also asks us to draw the Lewis structure. So remember, the carbons always make up the backbone. So I would draw out the carbons first. So there's 4 carbons in this molecule, and I draw all of them having 4 bonding arms. Of course, they're all connected by one of those bonding arms. And then all of these extra ones are where you're going to attach all those hydrogens. You can double count to make sure that there's 10 of them, and there are. Same thing for this cyclohexane right here. It's got 6 carbons, and we're going to draw them connected in a ring in a cyclic structure, so they look like in a hexagon shape. And each of those carbons is going to have 2 hydrogens attached to it, so the Lewis structure would look like this. So always remember with organic molecules that carbon makes up that backbone, that the center, and then the hydrogens are always on the outside, on the periphery. So Lewis structures are great for representing the connections that atoms have to each other in a molecule. But as we saw with the previous 2 examples, I animated them into here because it's tedious to draw them. And organic molecules can become very large, and that makes it difficult to draw. And so we have a couple of different shorthand techniques. So I'm going to, on this slide, show you all the different ways of viewing molecules. So the simplest way is to just show the molecular formula. Now this only gives us a very small amount of information. It tells us how many carbons and hydrogens there are, but it doesn't tell us necessarily how they're connected. It might tell us whether it's a straight chain versus a cycloalkane. In fact, this one here, C3H8, would that be a straight chain or a cycloalkane? Hopefully you said straight chain because it matches that CnH2n plus 2 formula. Right? Another way that we can write things out is using this condensed structure, which is a shorthand structure we're going to learn how to do, and skeletal structure, which is like an uber shorthand structure that we're going to learn how to do. That's very popular in organic chemistry. And then this ball and stick model, I'm just throwing it up here to show you. Usually you're not asked to draw that kind of model, but it's in a lot of organic chemistry classes you will actually purchase a molecule, like a modeling kit with balls and sticks, so you can build the molecules and see them in 3 dimensions. Because remember, Lewis structures, they're a great way to show connections, but molecules in real life are not 2-dimensional, they're 3-dimensional. And so in organic chemistry classes, it's usually important to visualize that and keep that in mind. So a lot of textbooks will at least show pictures in ball and stick form. So you'll see that in this class. But what we're going to talk about in this chapter is how to go from Lewis structures and convert them into condensed structure and skeletal structure. So the first one, condensed structural formula. In condensed structure, you kind of collapse all of those bonds and you just write the carbons with the hydrogens that they are connected to. So you're listing out the atoms right to left in order of their connection. All right, so the condensed structure here, CH3, CH2, CH3, represents this Lewis structure here. I like to think of it as like if you were to draw these sort of imaginary lines here between each carbon. All right, the first carbon has 3 hydrogens bonded to it, so we write CH3. The second carbon has 2 hydrogens bonded to it, CH2, and then the third one again has 3, so CH3. So even though we have these H's written in between the carbons, we know that carbons never go in the middle. They always go around the periphery. So we know that even though it's written CH, 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 that those connections are between the carbons. So there's that these 3 carbons are actually connected together as sort of the spine, and that those hydrogens are around the periphery. Not like this, not C, H, 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 all in a row. Okay, so it does require you to have that sort of understanding of chemical bonding. But I like to sort of imagine it as sort of chunking up the molecule. So let's do some practice problems. We have some Lewis structures, and we're going to convert them into condensed structure. This might be a little tedious with my trackpad. So first, I like to draw my little imaginary lines here, sort of the beginner's method of drawing it. So first, I've got this carbon here. We've got this carbon that has 3 hydrogens. So we're going to write CH3. And then next, we've got a carbon with 2 hydrogens. So it's a CH2. And then we've got another carbon with 2 hydrogens, CH2. Oh, and we got one more carbon with 2 hydrogens. So we have 3 of these CH2s. And then the last one, this 5th carbon, has 3 hydrogens, so CH3. So you notice in a straight chain, all of the central carbons have 2 hydrogens, and the ones on the ends have 3 hydrogens. It's always good to double check and double count this molecule. The Lewis structure has 1, 2, 3, 4, 5 carbons, and my condensed structure has 1, 2, 3, 4, 5 carbons. So you don't want to lose count there. Another way you could write this, that's even a little bit more shorthand, is to chunk all of those CH2s together. So we have a CH3, and then instead of writing CH2 3 times, especially if this was a longer molecule, oops, we write C, it's not an E, it's a C, CH2, and then we indicate that we have 1, 2, 3 of them outside the parentheses here, and then we write our closing CH3. So that's an even shorter hand way to write it, to bundle all those CH2s together in the parentheses. So both of these are correct ways to write this molecule in condensed structure. Both, either or, would be correct on a test. And you may see it written one way or the other way in the textbook, so you kind of have to know them both because you'll see them both ways. Now for this one, I'm going to take this chain here and I'm going to break it, put my imaginary lines there. So I've got 3 carbons in this chain. And I'll come back to this one up here, but I'm first going to draw those 3. So we've got CH3, and then the second one is CH, and it does have that thing branching off of it, so I am going to draw a branch point. So sometimes when you have branches or if you have double bonds, as you can see down here, those are bonds that you will see in a condensed structure that will be drawn. But all of the sort of bonds between straight connected carbons, we just get rid of. And then this third one here is CH3. So I'm writing that. And then that group that is sticking up is a CH3. So I'll write that CH3 up here. All right, so in this case, in the condensed structure, we are showing where those branch points are. We are drawing the bonds there. So this is one way to do this. Another way to draw the same molecule is to put the branch group in parentheses. So to write CH3, and then CH, and then instead of drawing a branch point, putting in parentheses that CH is also bonded to a CH3 group that's sticking off of it, and then connected to that CH3 at the end. So again, both of these are kosher ways to write the condensed structure of these Lewis formulas. In this bottom question, it asks us to go in reverse, to go from condensed structure to Lewis structure. All right, so I'm always going to start with that carbon backbone. In this, we've got 4 carbons attached to each other. So we've got carbon 1 connected to carbon 2, and then carbon 2 and 3 are connected by a double bond, and then this one, since there's no bond shown, I assume it's a single bond connected to that 4th carbon. And now I just have to draw in the hydrogens. And that's really tedious with my trackpad. I think I'll go for it anyway. So there's 3 hydrogens on this guy. This one has 1 hydrogen. I'm going to draw it sticking up. Could I have drawn it sticking down? Sure. This one also has 1 hydrogen. I'm going to draw it sticking down just for fun. Could I have drawn it the other way? Sure. And then this last carbon has 3 hydrogens. So draw it like this. Ta-da! So there's the Lewis structure. Of course, it takes a little bit more work to draw a Lewis structure. How about this one? This one's going to be fun. It has 1, 2, 3, 4, 5, 6, 7 carbons that I have to draw out. The ones in parentheses here represent a branch group that's coming off of this carbon here. All right, so I'm going to draw just the ones in the straight chain first, not the ones in the branch. So I'll do my carbon. There's 5 of them. Carbon, 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 and carbon. And this branch group is coming off of the 2nd carbon. So I'm just going to draw it up here. And it has 2 carbons in the branch. All right. And then I just have to fill in all the hydrogens, which is super tedious, so I'm not going to do that right here with my trackpad, but I'll show you where they're all going. So that one's a CH3. Here's a CH. In the branch, we have CH2 and CH3. So those would have those. This is a CH2, another CH2, and a CH3. So all of these, the ends of these lines, you would place an H for a hydrogen, and that would be the Lewis structure. So you can really start to see how condensed structure is much more convenient and less tedious to draw out, takes up a lot less space on the page than the Lewis structure, and still tells us how many carbons there are, what order they're connected in, and so on and so forth. So another even shorter hand way to write chemical structures is skeletal structure. And skeletal structure basically makes carbons and hydrogens invisible. So in skeletal structure, hydrogens are not shown at all. They are merely understood to be there. And the carbons are represented by the ends and bends of the lines. So you're just showing the bonds between the carbons here is all you're writing. I like to, my sort of beginner way of writing skeletal structures is to just put a little ball as a placeholder to show where carbons are at each of the ends and bends. So we can see easily there are 3 carbons here. And but notice there's no hydrogens. There's not even any bonds drawn to hydrogens. The hydrogens are completely left invisible. They're just understood, like we understand that this carbon must have 3 hydrogens because carbon must be bonded to 4 things and only 1 bond is shown. So that means there's 3 invisible bonds to hydrogen. All right, so let's practice some of these. Here we have some different compounds, some in Lewis structure and some in condensed structure, and we're going to draw them in skeletal structure. So let's start with pentane. We have 5 carbons in a row. So all we do is this. We draw a little ball for our carbon, connect it to the next carbon, 2, 3, 4, 5. And that's pentane and skeletal structure. Easy peasy. It's just 5 balls with 4 lines connecting them. One of the reasons why I really encourage you to draw those little balls is because a common mistake that students will make is they will draw 5 lines. All right, but 5 lines would be 6 carbons. So if you have 5 carbons, they're connected by 4 bonds. So drawing those balls really helps you keep track of the number of carbons. You might want to double check that you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Cool. Butane. Here's the condensed structure of butane, which is a 4-carbon straight chain hydrocarbon or alkane. And we're going to draw this one with 4. Now, in this one, I started by moving my line up. It doesn't matter whether you draw your line up first or down first. So for this one, just to make it different, draw the line down. Second carbon, third carbon, fourth carbon. Done. There's the skeletal structure. For cyclobutane, again, we're just drawing the carbons and the bonds between them. So a cyclobutane is going to look like this. So cyclic alkanes, when drawn in skeletal structure, just look like geometric shapes. Cyclobutane, which has 4 carbons, looks like a square. The one with 5 carbons, cyclopentane, looks like a pentagon. Cyclohexane is a hexagon, and you get the picture. All right. Now, of course, being able to do something means you need to be able to do it both directions, right? So I don't want you to just know how to go from Lewis structure to skeletal structure, but also from skeletal structure to Lewis structure, or skeletal structure to condensed structure. This is true in all languages, and chemistry really is its own language in a lot of ways. But like if you were studying French, for example, you need to be able to do your flashcards in both directions, right? If you are given the French word, you need to be able to say it in English. And if you're given the English word, you need to be able to say it in French. So it's always important to practice things in reverse, both ways. All right, so we've got a skeletal structure here. And again, I'm going to draw those little balls to represent the carbons, just to make them easier to count and to see. And what I have here is a branched chain alkane. So I have 5 in a straight row, and I'm going to write those 5 first. So the first one here is got to be a CH3. It's at the end. The carbon only is shown with 1 bond coming out of it, which means there's 3 invisible hydrogens there. The second one has 2 bonds shown, which means there's 2 invisible hydrogens here. So that's a CH2. And then this third one has 1 invisible hydrogen coming out of it, CH. It also has a branch coming down, so I'm going to draw that as a placeholder, but I'm going to keep doing this main chain first. So this next one is a CH2. There's 2 invisible hydrogens there. There's 2 bonds shown, so 2 are invisible. And then on the end here, the ends always have 3. We know that because this carbon only has 1 bond coming out of it, and it needs to have 4. So there must be 3 invisible hydrogens here. So I've drawn that sort of main chain. I'm going to come back to this, this branch point, or what we might call a substituent. And we've got a CH2, and we have a CH3. CH2 connected to a CH3. And that would be the correct condensed structure for this molecule. You could also do it where instead of having the branch there, that you have CH2 and CH3 in parentheses embedded right here. That's another correct way to do it. This is an example of an organic molecule that has another It's not just a hydrocarbon. It doesn't have just carbon and hydrogen. So carbons and hydrogens in skeletal forms are the only things that are sort of shorthanded. But if you had like an oxygen or a nitrogen or a chlorine, you just have to draw that symbol in. So here, all the N's and bens are carbons, except for that end that actually ends in a chlorine. This is a chlorine. All right, so we have 5 carbons. The first one on the left has 3 invisible hydrogens, so it's CH3. The next one, CH2. The third one is CH. It has 3 bonds coming out of it, so that means it has 1 invisible hydrogen. It also has a chlorine coming off of it. And I've drawn the chlorine sticking up. Even though it's sticking down in the skeletal structure, it doesn't matter. The direction doesn't matter. They're still the same molecule. The fourth one in the chain is a CH2, and then the last one is a CH3. All right, so we've practiced drawing skeletal structures, drawing some condensed structures from skeletal structures. You do need to practice this, and I encourage you to practice it on paper. When you're doing the homework in Chem 101, practice drawing these on paper. Definitely practice some problems from the textbook because you're going to need this muscle memory for drawing for the test, because the short answers on the test, of course, are hand-drawn. So now that we can draw these different alkanes, now we're going to learn how to name them. And there's a systematic process for naming things in science, and we call it nomenclature. So in biology, nomenclature is giving Latin names to different species, right? And in chemistry, it's giving, I guess, Greek or Latin names to different chemical compounds based on their structure. So chemical names sound really complicated. They're a mouthful, as you'll see, but they actually make a lot of sense when we break it down and we see that they're named based on these rules. And it's important to have a universal naming system for biological organisms, for chemicals, because people all over the world are studying these things, and they need to make sure they're using the same language, so that if somebody in China is studying a compound and somebody in Brazil is studying the same compound, that they're using the same name for that compound, so that when they publish, they can read each other's papers and know that's the same molecule. If everyone gave it everything their own name, then you wouldn't know in the published journals which molecules were the same as yours. So this table here is one that you might want to star in your notes, because you'll need to come back to it. In like an organic chemistry class, you would have to memorize these different sort of prefixes here. For every alkane, depending on the number of atoms, we use a specific prefix. So for 1 atom of carbon, the prefix is meth. For 2, it's F, 3, prop, so on and so forth. Once we get to 5, we start seeing some familiar shape prefixes, right? Pent for 5, hex for 6, so like a pentagon, hexagon, so on and so forth. So if it's a chain, a straight chain alkane with 4 carbons, we call it a butane. But if it's a branch group that has 4 carbons, we call it a butyl. So the branch groups end in -il, the chains end in -ane. So for example, in this molecule here, I have put a red line around the master parent chain, all right, which is the longest chain of carbons that we can find without having to pick up our finger and move it. So this one has 1, 2, 3, 4, 5. So we would call this a pentane. But then it has these branch groups coming off, these CH3 single carbon branch groups, which we call the substituents. All right, and those would be called methyl groups, not methane, but methyl, because they're substituents. And because they're sticking off, that means they have 1 less hydrogen than if it was just a straight chain with that number. So we're going to go through the steps of naming compounds. And I did reorder the slides a little bit. If you grabbed notes, printed notes, they will be in a slightly different order and format, but it's the same examples. So let's start with this simple one. The first rule is you want to find the longest continuous chain of carbon atoms. I'm going to call that the parent chain. I'm going to move my face around here. Okay, so the parent chain, can I change my pen color here? I can't. Okay, so the parent chain I'm going to do in red to match this. So the parent chain of carbons, and I'm going to also circle the hydrogens it's connected to. All right, so this is the parent chain. All right, and the parent chain is 1, 2, 3 carbons. And if we go back to that page before, we see that that's called a propane. So we put the parent chain's name at the end of the name of the molecule. So we're going to put propane here. We name the parent chain. Propane. All right. The next step is we need to identify the groups that are attached to the parent chain. In other words, those substituents. So I'm going to go to blue to match that. All right. So the only thing that's sticking off of it is this group here, a CH3, which is a 1-carbon group, a methyl group. So we're going to put that name here. We have a methyl group. All right. The other groups that you might see sometimes besides carbon or alkyl groups are you might see a halogen, like a bromine or a chlorine or a fluorine. And in that case, we just call it bromo, chloro, and fluoro, as the name of the substituent there. Right? If there's more than one substituent, more than one type of substituent, we are going to put them both there, and we'll put them in alphabetical order. But in this example, we just have the one. Third step is we need to number the carbons of the parent chain because we need to give this substituent an address. Where is that methyl group? Is it sticking off carbon 2, 3, 4, 5, 6, depending how many carbons you have in the parent chain. So in this case, we could number it this way, 1, 2, 3, and then that substituent be coming off of carbon number 2. Or we could label it this way, 1, 2, 3, and in that case the carbon's still coming off of carbon number 2. Okay, so it doesn't matter for this example which way we start numbering the carbon chain, but if it was a longer chain, it might, because we always want to start numbering it on the side that is closest to a substituent. So we'll see some examples where it does matter, but in this one it doesn't. And so no matter how you number that parent chain, that methyl group is on carbon number 2. And where's my pen options? Well, we're done here. This is called 2-methylpropane, and I would fuse these words together. Methylpropane just becomes one word. So we do put a dash between a number and a word. All right, so this is us assigning a number to each substituent. So it's sticking off carbon 2, so we put the 2 there. If we had 2 methyl groups, though, we would have to write, like if there were 2 methyl groups sticking off of this second carbon, we have to give them both an address of 2. So it would be 2, 2. And we would indicate that we had 2 methyl groups by adding a prefix, di. Or if we had 3, we would add tri, etc. So this is a very simple example. It's just 2-methylpropane. We're going to work our way up a little bit. So let's do this one. We're going to follow the same steps. First step, find the longest parent chain. So I'm going to use my red to match step 1 here. So we've got 1, 2, 3, 4, 5, 6. That might be the longest parent chain, but we're going to check all directions. 1, 2, 3, 4, 5. No, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there's a lot of different ways we could count try to find the longest chain, but no matter what, I seem to be just getting 6 as the longest chain. So I'm going to circle one that's relatively straight. And I just like to circle it to sort of show that I'm already naming this part. So when I name the parent chain, it's 6 carbons long, 6 carbon. Alkane is a hexane. So I put the name of the parent chain here. Hexane. All right. Now I need to find the substituent groups. I'm going to color these in blue. All right, so there's the rest of the stuff sticking off this parent chain. There's a group right here. There's a substituent group right here. And there's the substituent branch group right here. All right, and I want to name each of these. So I'm going to name this one is a methyl. I'm just going to put meth. This one's also a methyl, CH3. So I'm looking back at that table and I'm seeing what these groups are called. And the second one has 2 carbons. So this is an ethyl group. And I'm just going to write F for short right here. All right. So I want to list these different substituents in alphabetical order. Ethyl, E, comes before methyl, M. So I'm going to write ethyl first. And I'm going to leave a space. And I'm going to write methyl here. Methyl. All right. And then I need to give everybody an address. Before I do that, though, I guess maybe I should probably move this last rule up. All right. There is more than one methyl group. There's 2 methyl groups. So I do need to add that prefix di in front of methyl. No, lost my text. Oh, let's just redraw this real quick. All right, in red, we had our parent chain here, and that was a hexane. And then we said we had in blue, we have 2 methyl groups, and we have an ethyl group. Ethyl comes before methyl in the alphabet, so we wrote ethyl. And then we left a space and we wrote methyl. So you're kind of building the name backwards in a way. You start with the parent chain, but you put the parent chain name at the end. Ethyl, methyl, we actually have 2 methyl groups, so we need to use that prefix di to indicate there's 2 methyl groups. So now even though D comes before E, we don't count the prefix in that alphabetical order. We're just putting the groups in alphabetical order of their group name. And that di just tells us there's 2 methyl groups. All right, and then the last thing we need to do is to give them an address, basically assign them to a number carbon. So we could start numbering over here of our carbons, and we have 1, 2, 3, 4, 5, 6. If we do that, then the first carbon that we get a substituent on is carbon 3. Okay? But if we label it the other way, 1, 2, 3, 4, 5, 6, then our first substituent would be coming off of carbon 2. So you always want to have the lowest address possible for things. So we'd rather have our first substituent on carbon 2 than on carbon 3. we want it to start labeling on the end that's nearest to a substituent, and that's the right side. So we're going to use this right to left numbering system. So our 2 methyls are both sticking off of carbon number 2. All right, so we're going to say 2, 2 dimethyl. So we're giving each of those, we're listing the address for each of those methyls. They're both on carbon 2, so we just write 2 twice. And the ethyl is coming off of carbon 4. So we write 4 ethyl. So when you're doing the homework, they will be sticklers about this sort of punctuation here. So a punctuation rule for you that I'll add. Pen color, we'll do gray. All right. If it's a number connected to another number, so like we have 2, 2 right here, we separate it with a comma. So numbers are separated with a comma. And if it's a number followed by a letter, it's a dash. All right, and I'll just put the letter A. So it's 4 dash ethyl, number, dash letter, dash 2, comma 2 dash dimethyl. So we have dashes separating numbers and letters, and we have commas between 2 numbers. On a test, I won't hold you to that. I'm not going to be picky. I just want you to know the process. But on a homework problem, it will ask you that. All right, and the last one, which is a little bit more complicated. We're just increasing in complexity here. And we'll pause for a Tums break. Get all my steps lined up. First thing we're going to do is find our parent chain. All right, this chlorine is not part of the parent chain. The parent chain is only carbons and hydrogens. This one is in skeletal structure. So we had one, I don't know if you noticed, but the first one was Lewis structure, the second one was condensed structure. This one is kind of a hybrid, actually. All right, so this should just be a dot here, but they drew out the CH3. Okay, this one's a little confusing. So I'm just going to draw a line around the parent chain. This is the longest chain. I didn't count it out. I can count it out. This is the longest straight chain of carbons that we can find. 1, 2, 3, 4, 5, 6. This carbon is our 6th one. So that's a hexane. So I'm going to start. The first thing I do is write the name of the parent chain at the end of the name. Then I'm going to identify substituents. I like to do that color-coded in blue. So I've got CH3, a CH3, and a chlorine. All right, so the chlorine, we call that chloro. It's the name of that substituent, chloro. And each of these will be methyls. Methyl groups. So we have 2 of those. All right, which comes first in the alphabet, chloro or metho? Chloro. So we're going to write chloro first. Chloro. And then we're going to write methyl. And we're leaving that space so that we can write their addresses, their carbon numbers. But for methyl, since we have 2 of them, 1, 2 methyl groups, we need to write that by using the prefix di. And now in green, I'm going to label the carbon numbers. So we want to start with the side that is closest to a substituent, and in this case the left side is, because this carbon right here is already bonded. It's got a substituent coming off of it, chloro. So I'm going to label it this way, left to right. 1, 2, 3, 4, 5, 6. I'm just labeling all of the carbons in that parent chain so I can give those substituents an address. Chloro is coming off of carbon 1 dash chloro, and the methyls are coming off, one's coming off of carbon 3, the other's coming off of carbon 4. So I'm going to do dash 3, comma 4 dash dimethyl. I didn't really leave myself enough room here, so that's why I drew it like that. And so this would be called 1-chloro-3,4-dimethylhexane, which is a mouthful. These molecules look like so complex to name, but it's really just a set of steps and rules that we follow, and it actually gives us the exact directions for building this molecule. So we'll do some practice naming, but you also will have ones where you'll be given a name and you have to draw it, and we'll see how useful the name is there. So let's just do a couple more. These require a lot of practice. So practice, practice, practice. Here we go. We've got the longest chain I can count here is 5 carbons. So I'm just going to trace over my parent chain here. And then I'm going to also go ahead and identify what my substituents are. I like to do that in blue. So I've got a Cl, and then I've got this guy down here, which is a carbon with 3 hydrogens. All right, and those are my substituents. So now I'm going to name it. So my parent chain, in red, my parent chain 1, 2, 3, 4, 5 carbons. I look at the table, and a 5-carbon alkane is called a pentane. So I'm going to write that out first. It's a pentane. I have 2 substituent groups. I have a chloro and a methyl group. So I'm going to write those in blue. Feel free to do your own color coding. Chloro, methyl. Chloro comes first in the alphabet. So I'm going to write my chloro, and then methyl. It's a little bit of a tight squeeze for me here. Chloro and methyl. And then the last thing, of course, is to assign everybody numbers. I like to do that in green. So if the side of the parent chain that's closest to a substituent is the right side. So I'm going to start numbering here. 1, 2, 3, and then this would be 4 and 5. But this is enough to give me my addresses. The chlorine is on carbon number 2, 2-chloro, and the methyl group's coming off of number 3. So I'm going to do chloro -3 methyl. It's a funky looking 3. So this is called 2-chloro-3-methylpentane. This one here, this Lewis structure, we're going to find the parent chain. In red, we're going to count it a couple different ways. 1, 2, 3, 4, 5, if we go straight. 1, 2, 3, 4, 5, if we go this way. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. No matter how I do it, I seem to get 5 carbons. You won't always find that the parent chain is this, is the horizontal chain here. Sometimes you have a parent chain in a zigzag. So you do want to count. You always want to count and not assume. So this parent chain has 5. This is also a pentane of sorts. Pentane. The substituents, I'm trying to change my pen color and I'm having like brain farts here. Okay, here we go. In blue, we got this CH3 group that I kind of bulldozed over a little. And down here, a 2-carbon group, an ethyl group. So we have a methyl and an ethyl. Which comes first in the alphabet? Ethyl. So we're going to write ethyl, and then methyl, leaving a space between them so that we can write our carbon number address. Change the pen color to green for my address. Which side is closer to a substituent? It's the right side. It's closest, so we're going to start labeling on the right side. 1, 2, 3, and again I could keep going, but I don't have any substituents over there, so I'm going to stop. 1, 2. So carbon number 2 is where our methyl is. So we put a 2 in front of the methyl, and carbon number 3 is where our ethyl is. So this molecule would be named 3-ethyl-2-methylpentane. And it's important, little things like putting it in alphabetical order is important, because if you didn't, 2-methyl-3-ethylpentane would be a different name. And if you were looking for, like, Google searching for stuff about that molecule, you would think you'd think it was a different molecule. So it's really important that IUPAC rules are followed so that everyone's calling a molecule by the same name. And then lastly, this last one has a little curveball because it includes a cycloalkane. So for a cycloalkane, we count it as its own sort of unit. So even though we could count around the cycle, we could go 1, 2, 3, 4, 5, 6, 7, 8, 9 without lifting our finger. All right, the cyclo part is its own unit. So this has 6 carbons, and that's the longest chain because this has 1, 2, 3. All right, so our parent chain here is our cycloalkane, and it's cyclic, so we have to use that cyclo. We can't just say it's a hexane because it's not. It's a ring of, so it's a cyclohexane. Cyclohexane. My cat's getting into mischief over here. Might hear some stuff crashing down in a minute. And then our substituent groups. We've got this one here. I'm going to draw my little ball. It's a carbon with 3 hydrogens. That's a methyl group. And this one is a substituent with 1, 2, 3 carbons. And we call that, if we go back to the table, we call that a propyl group. Which comes first in the alphabet? Methyl or propyl? In this case, methyl does. So we're going to write methyl first. Methyl. And then propyl. Didn't leave myself a ton of space there. And then, of course, in green, we will do our addresses. We're going to label the carbons in this ring. And again, we want to start labeling closest to a substituent. In a ring, you could start labeling here or here. You could start labeling at the substituent. And we generally want to label at the largest one first. So we would write our 1 here. And then we could go in either direction numbering, but remember we always want things to have the lowest address possible. So we're going to number the ring in the order, like in the direction towards the next substituent. So it would be 1, 2, 3, 4, 5, 6. But I'm just going to show the numbers here because that's the ones that are relevant to our substituents. So the propyl group is on carbon 1 and the methyl group is on carbon 3. So it would be 3-methyl-1-propyl-cyclohexane. All right, so it is tedious work naming things, but it is actually very important to understand because moving on in the class, you will have problems in the textbook that'll give you names. It'll give you the name of a molecule, and you have to be able to draw it and figure out what it is. Alrighty, so we spent the most time with those saturated hydrocarbons, the alkanes. They're all single bonded carbons. And we learned how to name those. Other ones we're going to talk about, but we're not going to learn how to name, are these other types of hydrocarbons, the unsaturated hydrocarbons. And they're unsaturated because of the presence of a double bond or a triple bond. So the unsaturated hydrocarbons are the alkenes, alkynes, and aromatics. Alkenes have a carbon-carbon double bond, at least one present. So here's an example of a very simple alkene. Alkynes have at least one triple bond, and our aromatics have a very specific structure called a benzene ring. It's a 6-carbon ring, and every other bond is a double bond. Another way, so this is the skeletal structure of a benzene ring. Another way to draw it is to draw it with just a circle on the inside, because these bonds can actually hop around. And so this is a way of just sort of showing that those double bonds actually can be sort of traveling within that ring. And then this would be the ball and stick model version of a benzene ring. So aromatics have a specific structure of a 6-carbon ring with 3 double bonds. If there's only 2 double bonds, it's not an aromatic. If there's only 1 double bond, it's not an aromatic. It has to have 3 double bonds, and it has to be a 6-carbon ring. So bonds can be single bonds, double bonds, or triple bonds. We talked about when we learned how to draw Lewis structures that a single bond is 2 pairs or 2 electrons that are shared. So a single bond is the sharing of 2 electrons. A double bond, therefore, is the sharing of 4 electrons. And a triple bond is the sharing of 6 electrons, because each bond represents 2 electrons shared, or 1 pair of electrons shared is another way to say that. So single bonds technically are a bit longer than double and triple bonds, and that's because if you think about what bonding really is, bonding is actually overlap of these electron clouds. So in a single bond, the electron cloud only overlaps a little bit to share 1 pair, but in a double bond, the electron cloud is overlapping more in order to share 2 pairs of electrons. And so as you have more bonds, the atoms are actually getting closer and closer together. The bond length is shorter and shorter. And the bond strength is going to increase. A triple bond is stronger than a single bond. And that's kind of, I think, common sense. All right. Some important alkenes that you may know of or be familiar with and not realize it. Beta-carotene is an alkene. It's a large molecule made up of all carbons and hydrogens. It has several double bonds throughout it. And notice the suffix, the name, beta-carotene, because it's an alkene. All right. Pinene, the scent of pine scent, is due to this chemical pinene, which is a hydrocarbon. It's all carbons and hydrogens, and there is the presence of 1 double bond. Same thing with limonene, that gives lemon peels that lemon smell. Some aromatics. A lot of aromatics, aromatic compounds are actually carcinogens. Benzene, the simplest aromatic compound, is a carcinogen. It can cause cancer. A lot of the carcinogens in cigarette smoke contain lots of aromatic rings. So here are some examples of some aromatic structures in our world around us. So the only type of problems I'll ask you to do here is to basically identify types of hydrocarbons. Is it an alkane, alkene, or alkyne? And so another way that I like to sort of remember it is it goes in alphabetical order. Alkane, alkene, alkyne. Alkane is single bonds, alkene is double bonds, and alkyne has triple bonds. And then the 4th type, aromatic, is its own thing. All right, so this first one here, I see a double bond here. That tells me that this is an alkene. I'm just going to write ene. This is an alkene. It just needs one double bond to make it an alkene. This one here, naphthalene, is a little bit misleading by its name because it ends in ene, but I do see a 6-carbon ring with 3 double bonds. So this right here is an aromatic ring. So this would be aromatic. Aromatic. All right. And this one here, I don't see any double bonds or triple bonds or rings of any kind. So this one would just be a simple alkane. And you can see that in its name, isooctane. So sometimes if you're given a name, that's a giveaway, but sometimes it can be misleading. So you should be able to look at the structure and identify alkene, alkene, or alkyne, or aromatic, and know that those all four of those things are types of hydrocarbons, molecules made of just hydrogen and carbon. All right. So we said that these alkanes and these hydrocarbons are the most basic class of organic compounds, just containing carbon and hydrogen. But there's a ton of different organic molecules that contain additional chemical groups like halogens, chlorine, fluorine, or oxygen, or nitrogen. And those different chemical groups give the molecules new properties, different properties. And the molecules that have similar groups have similar properties. So we call these different groups or chemical add-ons functional groups. All right, so for example, one functional group is this OH group here. And OH is called the alcohol family or the alcohol functional group. And so you could have several different alkanes that have an alcohol sticking off of them, and they'll have similar properties because that group, alkanes are kind of boring. They're not, they don't do a lot of stuff, carbons and hydrogens, but OH groups are very polar, and they get into some trouble and like to react with things. So any molecule that has an OH, alcohol groups like to engage in certain specific chemical reactions. So these molecules we would say are part of a family. They're part of the family of alcohols because they all have an alcohol functional group. And like, in a family, people all kind of look and behave similarly maybe. And so same thing with chemical functional groups or chemical families. So there's a bunch of different functional groups in organic chemistry. And this is just a infographic from the internet that lists a whole bunch of them. You do not need to know all of these. I have starred ones that you will learn in this class. We've already talked about alkanes, alkenes, alkynes. These are not truly functional groups. These are just the family of just plain old hydrocarbons. All right, but alcohol, that OH group, is a functional group. An ether is just an oxygen that's squeezed between 2 carbons. So you'll notice that all of these have an R, all right? They have an R group. So R, if you look at your periodic table, is not an element, all right? We use the letter R to mean rest, as in like the rest of the molecule. And it's usually carbon groups. Others that we'll talk about, proteins have amide is how you pronounce it, amide groups. A nitrogen containing group coming off of a carbon is called an amine. So there's various different ones in your textbook that are listed. And really, it's just a form of pattern recognition. If you ever, when I was little, I used to like Highlights magazine, and they always had the hidden pictures activity where you had like a big busy picture and then there was like a little key It was like find the banana, find the shoe, and they're like hidden in the picture and you have to find them, right? So that's how I think of functional groups, the types of problems you guys will have, is it'll give you a big molecule and it'll say find an amine, or where's the alcohol, or what is this functional group called? And it's just kind of like comparing it to this table. So again, and not this table, but I would use the one in your textbook. And the table is more simple in the textbook. It's not all of these groups. So let's do just a little practice problem here where we practice just drawing some functional groups. So it says on this following alkane here, this alkane chain, we want to add the following functional groups to the missing spots. So we want to add an alcohol group. So we need to go to the table and look up what is an alcohol group. An alcohol group is an OH. So we're going to draw an OH group here, and I didn't say where, so you can just draw it anywhere. All right, I'm going to draw it here, OH. Notice that I connected the O to the carbon, okay, because H needs to be always out on the end, on the periphery. So you couldn't have H that was connected to carbon and oxygen. So the oxygen is the part that's going to connect to the rest of the molecule. A methyl group, that's an alkyl group. Not really truly a functional group. Well, it can be, so we're going to draw it. We'll just draw it right here. CH3, our methyl group. And then amines, if we go back to that table, we'll see an amine group is an NH2. All right, so we're going to draw it right here. An amine is a nitrogen and hydrogen containing group. And NH2 it is, right there. All right, so the problem could give us this molecule and say, circle the alcohol group, put a square around the amine group, and you would just be identifying them based on a list that you don't have to memorize, that you can reference. Okay, it's just about pattern recognition. We won't get into what all of these functional groups do chemically, but know that they do have specific chemistries, and that's what most of an organic chemistry class is focused on, just like sort of exploring the different chemistries of the different functional groups. So here's an example where it gives us a molecule, and this molecule happens to be glutamic acid, which is the parent compound. It's how we make MSG, monosodium glutamate, which is a taste flavor compound. And this is the structure of it. It says, name the functional groups you recognize in this model. So here's the sort of hidden pictures activity. Can we figure out where all of these functional groups are? So basically I'm looking for anything that's not a carbon or hydrogen. So if I see oxygens, I'm like, oh, that's a functional group. I go back to my table and I see that there's a carbon. This is a carbon double bonded to an oxygen and single bonded to an OH. All right, that whole thing there matches a functional group called a carboxylic acid. Carboxylic. So hopefully you can look at the one in the lecture notes or look at the one in the textbook. There's one in chapter 4. There's also one in the very back cover of the book. And clearly says that this functional group is called carboxylic acid. All right, and there's another one of these right over here. Another COOH is how another way that it's written. Like in condensed structure, it's often written COOH, and that's also carboxylic acid. Another one that I see is a nitrogen-containing group. I'll give it a different color. My pen. All right, this group right here, NH2, and we reference that table of functional groups, and we find that this is called an amine group. All right, so that's all it's asking you to do, is just find functional groups and name them. So when we have organic molecules, remember we said that you could have a molecular formula that tells you the number of carbons and hydrogens, but it doesn't tell you how they're connected. And it turns out they can be connected in multiple different ways. You can have a straight chain or a branch chain molecule, or maybe multiple different branch chains from a single molecular formula. So when you have two compounds that have the same molecular formula, the same number of carbons and hydrogens, for example, but different connectivities, different structures, we call those isomers. Iso means same. So they're same in that they have the same molecular formula, but they're different because they have different connectivity or different structure. This one is a straight chain of carbons, and this one is a branching chain of carbons. These are two isomers of butane. Right? So you might have a practice problem that just asks you to, are these two things isomers, yes or no? And the two things you're trying to address is, do they have the same molecular formula? If they don't, then they're not isomers. So the first criteria is, do they have the same molecular formula, and do they have different structures or connectivities? So in this first one here, first I want to address, do they have the same molecular formula? So this one has 1, 2, 3, 4, 5, 6, 7, 8 carbons. So I'm going to write C8. And I'm going to count the carbons in the second one here. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 carbons here. Well, they have the same number of carbons, so they have the same number of hydrogens. I'm going to just sort of draw little lines to show where those invisible hydrogens are. So each of these sort of corner ones has 2 invisible hydrogens, and each of these ends has 3 invisible hydrogens, and these intersections here, these branch points, have 1 invisible hydrogen. So I've got 2, 4, 6, 8, 10 plus 6, so that's 16 hydrogens, which is consistent with a cycloalkane formula. This one too, let's count those invisible hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these do have the same molecular formula. And they do have different shapes. This one is a cyclohexane with 2 arms, and this one is a cyclohexane with 1 long arm. So these are, in fact, isomers. Giving it a check. Let's check that it's an isomer, this pair. We would say they're isomers. They have the same molecular formula, but different structures. How about B? 1, 2, 3, 4, 5, 6, 7. First thing I want to do is count carbons to see if they have the same molecular formula. 1, 2, 3, 4, 5, 6. All right, so I don't even need to count the hydrogens here. These two molecules don't have the same number of carbons. They can't have the same molecular formula. So they are not isomers. They are just two different compounds that aren't the same at all. And then lastly, C, we've got 1, 2, 3, 4, 5, 6 carbons. C6. And this one is 1, 2, 3, 4, 5. All right. So if this had a 6th one here, then these are going to be isomers, but it doesn't. It has different numbers of carbons, so again, we would say these are not isomers. They're just two different compounds, unrelated. Okay, so isomers have the same molecular formula, but different structures. So that's sort of the basic definition of an isomer. Sometimes you have these more subtle isomers. So these were all fairly visible just by looking at them. You could tell that they had different structures because they were connected in a different order. But sometimes you can have atoms that are connected in the same order, but they are oriented differently in three-dimensional space. And we call these sort of three-dimensional isomers, they're called stereoisomers. They're not obvious in 2 dimensions a lot of times, but they are obvious in a 3-dimensional molecule. So the first type of stereoisomer is a cis-trans isomer. And these occur only if you have double bonds or a ring, a cyclic alkane. And that's because those types of molecules can't rotate. You can rotate around a single bond, right? A single bond can have rotation. And so groups on these 2 carbons, if my hands are the carbons, they can rotate around. But if I have a double bond, okay, I can't twist because those double bonds are strong and they don't twist. You can't twist a double bond, you would break it. Okay, so if you have groups sticking off of carbons, like if I have groups sticking, if my pinkies are substituent groups sticking off here, all right, if they're both sticking down, they're stuck sticking down, they can't rotate. So if I had one that had a group sticking down and the other had a group sticking up, that's different. They can't rotate, and that's a different arrangement. All right, so in a cis isomer, the 2 groups are both sticking up, and in a trans isomer, well, or not up, they could be sticking down. They're both sticking in the same direction on the same side of the double bond. In a trans isomer, the groups are on opposite sides. I'm trying to like do my little cheerleading moves, but I can't fit. So cis are on the same side. They're both sticking on the same side, either up or down. And in a trans isomer, they're sticking in opposite directions. Okay, so the word cis means same, and the prefix trans means opposite. That's why they're called cis isomers and trans isomers. So my little technique for this is to sort of draw an imaginary line between, like through the double bond, and then sort of circle the groups. And if they're on the same side of that line, then it's cis. If they're on opposite sides of that line, then they are trans. So let's do a couple of practice problems here. So I'm going to do the bottom ones first. All right, so oops. We get our pen here, all right, and we draw this sort of imaginary line here, extend that double bond basically, and then we circle the groups. A hydrogen is not a group, okay? A hydrogen is invisible in skeletal structure, so we don't count that. We're not looking at the hydrogens, we're looking at any substituents really coming off. So in this case, the substituents are on opposite sides of that double bond. So this would be a trans isomer versus one like this here. We extend that double bond and we draw a line through it. We've got a substituent here and here. They are both on the same side of the line underneath the double bond. So this would be a cis isomer. Oh, my battery's dying. I gotta get my charger to plug it in so we don't lose this video. Okay, this is actually my 3rd take of this video. All right, we're good. Now let's do the top examples. So I'm going to do this one first. I'm going to take my pen and draw my line just to extend that double bond. All right, I've got a substituent here and a substituent group here. They are both on the same side of this line. So this would also be a cis isomer. And then for this one here, the double bond I care about, by the way, is the carbon-carbon double bond, not this oxygen double bond. That's part of a functional group, okay? And so my substituents would be this part here and this part here. They are on opposite sides of this line that I had to draw at an angle because of the way that the chain is drawn. So this would be a trans isomer. right? So for cis and trans, all you need to be able to do is if given an isomer, identify, is it a cis or a trans isomer? Are the groups on the same side of the double bond or different sides of the double bond? And remember, this is true for double bonded things, but it's also true for rings, for cycloalkanes. So there's a couple of different ways you might see these drawn. So for a ring structure, it might be drawn out flat in 2 dimensions like this, and then to show that one of the groups is sticking out towards you, you use a solid wedge, and to show it sticking out sort of back into the page, you should use this dashed wedge here. So these are both going in different directions. So this would be a trans isomer, and in this one on the right here, they're sticking out in the same direction, so that would be a cis isomer. Another way to draw rings is to draw them sort of laying like this on their side, and then showing the groups just up and down. So again, this would be trans because one group is sticking up above the ring, the other sticking down, and in this one they're both sticking on the same side of the ring, so that would be a cis. So these are cis isomers, trans isomers. Another type of subtle three-dimensional isomer is called an enantiomer. And enantiomers are very subtle. They look very similar. These two molecules here, they look like the same molecule, just mirror images of each other. But that mirror image thing is actually important. It means they are actually different molecules. And in fact, this version here is the taste and smell of spearmint, or it contributes to the taste of spearmint, which is like very minty. And its mirror counterpart is the taste of rye or caraway seeds. So if you've ever had rye bread, that very classic rye taste, which is nothing like spearmint, right? They're very different flavors, but the molecules are almost identical. The difference is that they are right-handed versus left-handed. So an enantiomer is defined as a molecule that is a mirror image but is not superimposable. And your hands are classic enantiomers. They are mirror images of each other, but if you try to stack them one on top of each other, all right, your thumbs stick out. They don't stack. All right, that's why we have a right hand and a left hand, and you have a right-handed glove and a left-handed glove, and they don't fit on the wrong hand, like a baseball glove. I don't know, maybe some winter gloves would be ambidextrous. But molecules can basically have handedness as well. So enantiomers are molecules that have handedness, and the sort of chemistry term for handedness is chirality. Chirality means that they have handedness. So in order for a molecule to have an enantiomer, to have handedness, it must have at least one chiral carbon. And a chiral carbon is a carbon that's bonded to 4 different things. So not like 4 hydrogens, all right, that would not be 4 different things. That would be 4 of the same thing. So it has to be bonded to 4 different things. And so I like these pictures for illustrating that. These molecules here are mirror images of each other. You can see if you look in a mirror, they're flipped. But if you try to superimpose them, all right, the blue group overlaps and the red group overlaps, but the green and white groups are flip-flopped and do not properly overlap. So therefore, there are right and left-handed versions. The left-handed version is, so unfortunately in this area of chemistry, this is an area where there were a couple of different naming systems. And so the left-handed molecules might be called L. L and D for left and right, D for dextro, which is right in Latin, or it might be called minus and plus, or it might be called S and R, and that's kind of confusing. L and D I have in bold. That's the one that's used most commonly and that we will use in this class for left and right-handed versions. But just note that in other textbooks you may see things labeled as negative and positive, or S and R. And I purposely include some examples in the next couple of slides using those naming systems. But what I want you to know is the L and D. L for left-handed, D for right-handed molecule. And we'll talk about how to identify whether it's left or right-handed in a later chapter. Okay, so whether molecules are left-handed or right-handed is chemistry-wise not all that important, because the left-handed and right, both of these molecules have the same exact chemical properties, the same boiling point, the same melting point, the same density, like they're going to have all the same physical and chemical properties. But where it comes into play is really important is in biological systems, because in biology we have enzymes and receptors that recognize specific enantiomers. They only fit either the right-handed or the left-handed version, just like your shoes fit into specific, or your feet fit into specific shoes. There's the right shoe and the left shoe, and your right foot doesn't fit properly in your left shoe, and your right hand doesn't fit properly in a left-handed glove. And so that in biology, that's where these chiral molecules or enantiomers become very important, because of chiral recognition, the ability of receptors and enzymes to detect specific enantiomers. So some real-world examples of chiral compounds in biology are a lot of smell and taste molecules have enantiomers, and they are perceived differently by our taste receptors or our smell receptors. So I already talked about that example of carvone. The left-handed, here it's labeled negative and positive, the left-handed version is spearmint flavored, and the right-handed version is rye flavored. Another place where this becomes really important is in drugs, in pharmaceuticals. So most pharmaceuticals are made synthetically. Even if they were derived originally from like tree bark or a plant, they're now made in a lab with pure chemicals and are synthesized. And when you synthesize a organic compound that has an enantiomer, you will automatically synthesize a 50-50 mix of each enantiomer. So when you synthesize a chiral drug, you're going to get what's called a racemic mixture, half left-handed and half right-handed. And remember, the left-handed and right-handed forms of a molecule may have totally different, they bind to totally different receptors and enzymes in living things. And so if you have a racemic drug that contains both left-handed and right-handed enantiomers, there's kind of two possibilities. One is that both of the enantiomers have activity. They both bind to receptors in the body, but only one of them usually has the desired effect, and the other one ends up being responsible for side effects, some of which might be undesired. And the other possibility is that one enantiomer has the desired function, and the other enantiomer doesn't bind to anything and is just like, washed out, and has no effect. And so chiral drugs have to be tested for these things. So some examples of each of those scenarios. Propranolol is a common beta blocker that's given to people who have high blood pressure or a cardiac arrhythmia. And there's enantiomers here. So there's the right-handed D-propranolol and the left-handed L-propranolol. All right. The D isomer has no activity. It doesn't bind to anything in the body. So it doesn't cause any side effects. There's no negative downside of it. It's the L isomer that actually binds to enzymes and has the desired effect. So it's okay to give people a racemic mixture of these two, because one of them is just basically like inert. It's a dud. It doesn't do anything. Thalidomide, though, is a very sort of infamous drug. It has some sedative and anti-nausea effects, And so when it was discovered, it started being prescribed as a sedative / anti-nausea medication. And what population suffers from a lot of nausea are pregnant women who have morning sickness. So in the 1950s, when it first came out, it became a popular drug to prescribe to pregnant women who were suffering from morning sickness. In Europe, I should add, the head of the FDA in the US at the time was a female, and she decided there wasn't enough research of the drug on pregnant women to decide it was safe, so she banned it from being prescribed to pregnant women. But in Germany and England in particular, it was heavily prescribed to pregnant women, and it wasn't until they had their babies that scientists realized that there were some negative side effects on fetal development. So it turns out that thalidomide is a racemic mixture. It's half and half right and left-handed versions of the same molecule. And the right-handed version is good at inducing sleep and reducing nausea, but the left-handed version is teratogenic. That means it induces birth defects. It causes birth defects. And the birth defects, what it did is it prevented limb development, or it truncated limb development. So babies were born with either shortened arms or shortened legs, or both. And it was a whole generation of babies that were born this way, and they're collectively known as thalidomide babies, that were born in England and Germany in the 1950s. And so the drug, of course, was immediately pulled and not given to pregnant women anymore. It is under, I think it's been licensed for use again, not for pregnant women, but it also works as an anti-cancer drug because it prevents angiogenesis, or blood vessel formation, and that's how it affected the limb formation, because it basically kills the vessels growing to feed the limbs so they can't grow, but it can also kill off tumors by not allowing them to grow new vessels to feed themselves. So sometimes you find a drug and it's toxic and you pull it off the market, but then you realize it can have sometimes those toxicities actually can have desired effects for other diseases. So this is just my slide showing you that if you've ever watched the show American Horror Story, which is not my thing because I'm not into scary horror stuff, but one of the central actors in it, his name's Matt Fraser, and he's really a big disabilities advocate. And he, if you watch his story, he's a thalidomide baby. He was born to a mother who took thalidomide during pregnancy, not knowing any better, and so he has these shortened arms, and it's due to thalidomide. And this is just my sort of jokey slide that I like to sort of think of stereoisomers potentially as these sort of like evil twins of each other. And I never saw this movie, Black Swan, but it's like Nicole Kidman, or what's her name? Natalie Portman's character has like an evil, I don't know, mirror image. And so sometimes like if you know someone and then you're like in another city walking around and you see someone, you're like, oh my God, I swear that was so-and-so. You might call them their doppelganger, like a paranormal ghost-like twin. All right, so I kind of think of sometimes that these enantiomers kind of act like evil twins. You've got like the good twin and then the evil twin that has the negative side effect. But those are enantiomers for you. And that is finally the end of Chapter 4 lecture. See you for the next one. Bye.